the question goes on asking you to graph y of 1x, then y of 1.5x, and y of 2x. Now we're just going to do y of 1x now because the pattern will be established. You can then easily enough do the 1.5x and the 2 comma x. Okay, we substitute 1, we get this, we rearrange it, we factor out the 4 pi, so now x is replaced by x plus 1/4. That is, the x in our original sine of 4 pi x is now x plus 1/4. That shifts the graph 1/4 of a unit to the left, so that our original graph y of 0x is here. Our graph y of 0.5x, which I depicted in smaller, well, I drew that smaller in green at the end of the last clip. Looks like this. We've shifted 1/8 of a unit to the left, and now the graph of y of 1x takes this graph and shifts it another 1/8 of a unit to the left. So this is going to continue. If we do y of 1.5x, we're going to have to shift another unit to the left. This part of the graph will be here, so 3/4 of this cycle will be to the left of the y-axis, or that is the y-axis. And then when we do y of 2x, as you should verify for yourself, you need to understand these functions, and the graph will shift another unit, another 1/8 of a unit to the left, so that this point will have shifted over here, and the whole thing will be here. So we see original graph, shift to the left 1/8 of a unit, shift to the left another 1/8 of a unit, then another 1/8, then another 1/8. So we can see the wave propagating to the left. I'll also comment that this wave, or this function, doesn't end here, and it doesn't begin here. This is just one cycle of the function that we're kind of tracing through this analysis. The function goes on here, and it goes on forever. Okay, so this function goes on this way, goes on this way, propagating this way. Now, when you're modeling a real wave, you're going to have to restrict the domain somehow, the t and x. You're only going to apply this for a certain domain in the tx plane. But we don't need to talk too much about that right now. That'll come out when we actually start analyzing specific situations. Now, we want to shift our attention, and we want to look at what happens when t is a variable, because we have a function y of tx. We've just looked at what happens to the function y of x, the space picture of the wave, the picture of the wave along a line as it moves in time. What happens if we hold x constant and change y? We can actually look at that with these three graphs. This point on the graph, the x equals 0 point, is here. Then 0.5 time units later, the x coordinate has gone from 0 here to 1 here. And then in another 0.5 units, it goes back to 0. And as the graph shifts to the left, this point will now shift over here, so that at time 1.5, another 0.5 units of time will have shifted, will have elapsed, and the x equals 0 point will have a y coordinate down here. And then another unit, and it'll be back here, because this point will have moved over here. So we see that there's this simple harmonic motion at x equals 0. Similarly, there's a simple harmonic motion at x equals 1/8. It starts now at t equals 0 here, and then it moves down to here, and then down to here. So we're up, we're at equilibrium, we're below equilibrium. Then we're going to come back up to equilibrium and back to this point by the time t equals 2. And every point of the graph does something similar. It goes through simple harmonic motion. And when we substitute a specific value of x, we obtain that simple harmonic motion. Okay, we obtain the equation for that simple harmonic motion. So that y of t 0 is the sine of pi t. You can verify that very easily. If x is 0, you get the sine of pi t. That's a periodic function with a period of 2. Well, we already knew that that thing had better have a period of 2, because in letting t go from 0 to 0.5 to 1 to 1.5 to 2, every point appears to have gone through a complete cycle. At least this point does, and this point does. And of course, we can determine that this is period 2 because in order to change pi t, to drive pi t through a complete cycle, t has to change by 2. Complete cycle being 2 pi. So if t changes by 2, the pi t changes by 2 pi, drives the sine function through a complete cycle. We can graph this. Now this is no longer a graph of something we can see in space. This is a representation of the motion of a given point, the x equals 0 point in time. And we see that as time goes from 0 to 2, the x equals 0 point goes from 0 to 1 to 0 to negative 1 to 1. Of course, that's exactly what we saw here. At t equals 0, the x equals 0 point is at 0, then it's at 1, then it's at 0, then it'll be at negative 1, then 1. Okay, so now y of t 1/8. Okay, that's sine of pi times the quantity t plus 1/2. That shifts this graph 1 unit to the left, and the interpretation is, well, at t equals 0, y is 1. Okay, well, that is what happens when x is 1/8. So we go over here to x equals 1/8, and we see, yeah, sure enough, at t equals 0, this thing is at 1. At t equals 0.5, this is down to 0, and that's exactly what happens. At t equals 1, we're down to negative 1. Well, when t equals 1, there we are. We're at the low point. So that what we have here then is a graph of the motion of the point at a given x coordinate in time.